Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwarrao, your physics faculty. Today we are about to deal with the session number 59, first year Neet. The chapter name is Laws of Motion. And in the previous sessions, we have discussed about all the three Newton's laws of motion and their applications were discussed. Momentum change was discussed and law of conservation of linear momentum was discussed and its applications too were completed. And in this session, I will start with frames of references. So what is frame of reference? Frame of reference. See, in physics, you always need something as reference to explain things. For example, if an object is moving, for example, myself, if I ask you what is my state of motion, all of you will say that I am at rest position because I am standing right before you, isn't it? But I am at rest position with respect to earth, with respect to ground, isn't it? If somebody is observing me from the moon or from outer space, then earth is in rotatory motion. Since I am on the earth, I will be in the rotatory motion. So am I at rest position? No. So with respect to a person, with respect to a observer, or with respect to a frame of reference which is in the outer space, I am in motion. With respect to a frame of reference that is fixed to the ground, I am at rest position. So it all depends on what frame of reference you are dealing with. That is going to give us a perfect picture of type of motion that a object is undergoing. And what is a frame of reference? So basically, the coordinate system that we take frequently to explain things is nothing but frame of reference. You can imagine XYZ coordinate system anywhere here to talk about my position. Okay, for example, if you imagine one coordinate system in that corner, okay, and if you imagine one x-axis along this direction, y-axis along this direction, and z-axis in the upward direction, you can talk about my coordinates. Because right now I am standing, according to this description, this is x-axis, this is y-axis, this is z-axis. So in which plane I am standing? I am standing in xy plane. I am standing in xy plane. So you can talk about xy coordinates, right? Maybe let us say my position is some 2, 5, something like that. If that is the situation, okay, that is what position with respect to this coordinate system. What if you imagine coordinate system somewhere there to that corner, fix origin to the corner and imagine these three axes, okay, then my coordinates will be different. So based on the coordinate system or frame of reference that we have chosen, my position is changing, isn't it? But I am at rest position only. I am at rest position. But with respect to all these frames of references which are fixed to this room, I am at rest position, isn't it? But what has changed? My coordinates, my position coordinates have changed. If my position coordinates changes, position vector changes. Okay. If a housefly is moving in this room, okay, if you want, you can fix one coordinate system somewhere there and you can study its motion. It's not like, always you have to fix coordinate systems to the corner of a room. You can fix anywhere. You can fix anywhere. Okay. For example, a person is on the ground. Okay. And that person is observing a bus moving on the road. Okay. So he can take anything as reference. Anything as reference. For example, if the person is sitting inside the bus, with respect to him, the driver is at rest position. So if a coordinate system or frame of reference is fixed to the bus, each and everyone, whoever is sitting inside the bus, whether the passengers or the driver or the conductor, all those people are at rest position. Okay, provided if all those people are sitting in their positions. Okay. If at all, if a frame of reference or coordinate system, if you imagine that one to be somewhere outside on the ground, on the road, or just beside the road, if you imagine a tree, and to that tree if you fix the coordinate system, and with respect to that all these people are in motion. So I hope you have got an idea what a frame of reference is. Frame of reference is basically a coordinate system with the help of which we'll be able to study the motion of bodies. Okay, so that's what we'll start with. There are two types of frames of references. How many types? Two types. One is called inertial frame of reference. Inertial frame of reference. The second one is called as non-inertial frame of reference. See, this kind of categorization, classification, these things are done based on something. Okay, like materials, you can classify based on their conductivity into semiconductors, insulators, and conductors. Okay, based on their crystallinity, you can classify them as amorphous solids or crystalline solids like that. You can based on type of crystal structure you are dealing with. Okay, so like that, based on something you can categorize materials. Okay, so here based on what frame of reference is classified into two types, if that is the question we ask ourselves. Based on the validity of Newton's laws, frames of references are classified into two types. Based on what fact? Based on validity of Newton's laws. In this inertial frame of reference, Newton's laws are valid, whereas in case of non-inertial frame of reference, they are not valid. And no need to panic if they are not valid. We can do some changes so that Newton's laws are valid in non-inertial frames of references also. Okay, so basically, if Newton's laws are valid in a frame of reference, we call that frame of reference as inertial frame of reference. If at all, if Newton's laws are not valid, we call that as a non-inertial frame of reference. I'll tell you why Newton's laws are not valid. I'll give you an idea about that. Okay, so where we are getting trouble with the non-inertial frames of references, in the validation of Newton's laws. Before that, let me talk about the characteristics of these frames of references. This is basically what a frame of reference where Newton's laws are valid. See, there are characteristics for an inertial frame of reference. One is inertial frame of reference is basically what unaccelerated frame, or a frame which is at rest or moving with constant velocity. A frame which is at rest or moving with constant velocity. Moving with constant velocity in the sense its acceleration is zero, isn't it? Its acceleration is zero. And the second characteristic of this inertial frame of reference is real forces will act. Real forces acts. I'll tell you what real forces are. See, real forces in the sense when one object is directly exerting some force on another object, such a kind of forces are called as real forces. Okay, so if I'm talking about real forces, definitely there will be unreal forces, right? Unreal forces. Okay, so I'll tell you about those things also. I'll give you details of these real forces, okay, a bit later. Okay, let us proceed. And here the characteristics of non-inertial frame of references are, first one, it undergoes accelerated motion. Okay, a frame which undergoes, what do you mean by frame undergoing accelerated motion? So wherever you imagine the frame of reference, for example, if you have imagined frame of reference to the earth, so with respect to all ground related activities, that frame of reference is at rest, and you can call that as inertial frame of reference, isn't it? But if you are observing the activity, some activity on earth from the outer space, and you have taken the same frame of reference as frame of reference, you have taken the same coordinate system as frame of reference from the outer space, and the frame of reference now it is fixed to the ground. In this case, it is non-inertial frame of reference, because when you are observing from the outer space, the earth is in spinning motion, isn't it? And it is in revolutionary motion around the sun. So these two things will make this frame of reference accelerated frame of reference, because when a body is moving in curved path, when it is spinning or when it is revolving around the sun, it is in curved path, right? So when it is in curved path, what happens? Velocity's direction changes. So you call that as accelerated motion, isn't it? So whenever we know that whenever a body is in circular motion, its velocity's direction has to change. Otherwise, it cannot maintain circular path, isn't it? Or curved path. So it is an accelerated frame, since Earth is spinning and it is revolving around the sun when you are observing from the outer space, and the frame of reference, if it is fixed to the ground. Okay, so such a kind of frame of reference is what? Non-inertial frame of reference. Okay, so a frame which undergoes acceleration, okay, is called non-inertial frame of reference. Okay, or you can write like this. So this frame undergoes this frame undergoes accelerated motion. Accelerated motion in the sense, again, uniform acceleration is possible, non-uniform acceleration is possible. Both kinds of accelerations fall under the category of non-inertial frame of reference. If a frame of reference is undergoing both accelerated motion or uniform accelerated motion or non-uniform acceleration, in both the cases we call that frame of reference as non-inertial frame of reference. Acceleration can be uniform or non-uniform. Okay, so both are possible. Now, what does it mean? Why these Newton's laws are not valid in non-inertial frame of reference? So let us look at that aspect. Okay. I will take one example. I'll describe one situation here. Let us say on the ground, here one observer is present. Okay. Now let us say here one car is in motion. Inside this car, let us say one observer is sitting. Okay. Let us say it is undergoing a acceleration equal to some A. Okay. So the car is going with an acceleration A, and this person is at rest position. Okay, and these two people are observing another body somewhere here. Okay, let its mass is m. Let this body is acted upon by some force along this direction. It might be acted upon by several forces, but the net force, let us say it is along this direction. Okay, so now this observer is observing this particle, and this observer is also observing this particle. So both are observing this particle. But here, what is the difference? One observer is at rest position. So the other observer is at what? Accelerated motion, isn't it? So I will fix one frame of reference to this person somewhere here on the ground. This is also at rest position. Okay, and I am going to fix one more coordinate system here. Okay, to this car. Like this, x, y. So now whatever frame of reference you have chosen, which is on the car, that frame of reference is moving with an acceleration a, and here the frame of reference is at rest position. So acceleration is 0. Okay, so according to our discussion, earlier discussion, this is inertial frame of reference and this is non-inertial frame of reference. So if I am trying to deal with Newton's laws of motion, in this frame of reference, Newton's laws are valid, and in this frame of reference, Newton's laws are not valid. Let us see what does it mean. It means, with respect to this observer, if you try to write acceleration of this body, yes, this body possesses acceleration because it is experienced with some net force, F, in this direction. So that acceleration A bar will be equal to F bar by M. That's what we write for acceleration with the help of Newton's second law of motion. So A bar is equal to F bar by M, isn't it? But with respect to this frame of reference, or with respect to this observer, this A bar is not going to be equal to F bar by M. Okay, it is not equal to F bar by M. That's why we say that Newton's laws are not valid in non-inertial frame of reference. Non-inertial frame of reference in the sense a frame of reference that is undergoing accelerated motion. So let us try to prove this. Okay, to make sure that it is valid, Newton's laws, Newton's laws, these are, to make sure that these laws are valid in non-inertial frame of reference, what we have to consider, what changes we have to make. Okay, so let us deal with that. So I will take another example. Let us say here, one frame of reference is present, and here also another frame of reference is present. Okay, x, y axis. Let us say this frame of reference, I will designate this at A. So this is frame of reference A, this is frame of reference B. Okay. Let us say in this frame of reference, there is a particle P, let its mass is m, and it is moving along this direction with some acceleration. Okay, we don't know how much is that its acceleration, but here whatever frame of reference B we have chosen, let us say it is undergoing a acceleration equal to a naught. Let us consider like that. Okay, now I'm going to talk about acceleration of this particle P with respect to coordinate system A. Here this coordinate system A is inertial frame of reference. Its acceleration is 0. So what I'm talking about, I'm going to talk about acceleration of the particle with respect to frame of reference A is equal to, using relative motion knowledge, how this can be written, acceleration of P with respect to A is equal to acceleration of P with respect to B plus, and this B is also undergoing accelerated motion, isn't it? So acceleration of frame of reference B with respect to A, isn't it? So this is moving, and inside this is also moving. That is the situation. But all that I am interested is, I am not interested in the acceleration of this one or this one. I am interested in acceleration of this particle, P. That's what we are supposed to deal with, right? That is what our primary concern is. So let us talk about acceleration of particle P with respect to B. Acceleration of particle P with respect to B. Okay, so in this frame of reference it is moving now. So let us talk about that. It can be written from this equation as acceleration of P with respect to A minus acceleration of B with respect to A. That's how it can be written. Okay. Now multiply with mass of the particle on both the sides. M A bar PB is equal to M A bar PA minus M A bar BA, isn't it? So what is this M A bar PB? This is what this acceleration belongs to, acceleration of the particle P with respect to B. Okay, so let us say it is experiencing some acceleration here. I'll consider that acceleration as A. I'll consider that acceleration as A with respect to this frame of reference. So let us talk about that. So A, and on both the sides I will divide with M. So when I divide with the M, what I will get? M A bar PA by M BA bar by M. And here, whatever force this is experiencing, that force is what? M A bar PA. Because in this this particle, total force experienced by that particle with respect to what a frame of reference A is nothing but mass into its acceleration, according to Newton's second law of motion. So here this equation, or A bar PB, can be written as F bar minus M A bar BA by M. That's how it can be written, isn't it? So here acceleration of particle P with respect to B, or with respect to the accelerated frame of reference, what is that? F bar minus M into A bar acceleration of particle P with respect to frame of reference A divided by M. In fact, if at all, if you are not aware of this fact that Newton's laws are not valid in non-inertial frames of reference, and if I ask you to write about its acceleration, what you will be writing directly? You will be writing this as A bar PB is equal to F bar by M. That's how we write it, according to Newton's second law of motion. This is the equation. But here, this A bar PB is not equal to just F bar by M. It is equal to F bar minus some other term is getting added here. Even that term also, it appears like a force term only, because mass multiplied with the acceleration, what is that? It's a force term only, isn't it? So some extra force is there. All that I know is there is a real force F acting on the particle. There is a real force acting on particle P, which is equal to F. That's what we were told. So there are several forces that are acting. Net force of all those forces is equal to what? F bar. So if I have to write acceleration of this one with the help of Newton's second law, this is what I will be writing. But when I deal with this, theoretically like this, what did I get? I get this one, isn't it? So here, Newton's laws are not valid in non-inertial frames of reference unless you consider this extra term. Okay, so this is what we have identified here. So this can be further written as acceleration of particle P with respect to B is equal to F bar plus minus M ABA bar by M. So here we are having sum of two forces. One force is real force, the other force we don't know what is that, because no body is exerting that force. No body is exerting that force, nobody is exerting that force. Okay, so such a kind of a force which is not exerted by anybody is called as unreal force, or this is precisely termed as pseudo force. What is this? Pseudo force. This is precisely termed as pseudo force. And this is what our further discussion is going to be, because most of the times we will be dealing with non-inertial frames of references, okay, for practical applications purpose. For example, if you are dealing with a lorry moving with accelerated motion and there is a block of mass, okay, on the truck, so it experiences some force. Sometimes even those, if based on what value of acceleration the lorry is moving, the stones or the blocks of masses may slide on the truck. So why is it happening? If suddenly bus starts, what happens? You will fall in the backward direction. You will experience a force in the backward direction. Who is exerting force on you? Anybody is exerting force on you, but you do experience force in the backward direction. Such a kind of forces are unreal forces. Such a kind of forces are called as pseudo forces. Such a kind of forces are called as pseudo forces. Okay, so unless you consider this pseudo force, you cannot make sure that validation of Newton's laws are possible in the frames of references. Okay, so I hope you have got an idea. All that you need to remember is, okay, in case of non-inertial frames of references, in case of accelerated frames of references, we have to consider an extra force called pseudo force. Then validation of Newton's laws is possible in such kind of frames of references. If you are dealing with simply inertial frames of references which are at rest position or which are moving with uniform velocity, no worries, no need to consider pseudo forces or unreal forces. You have to consider real forces only. Okay, so in case of, you can conclude like this. In case of inertial frames, if you wanted to write expression for net force, this is how it can be written. Simply add all the net forces, which is equal to mass into acceleration. In case of non-inertial frames of references, you have to consider both real forces plus unreal forces or pseudo forces. Okay, so from this one more conclusion can be drawn. Whatever this pseudo force is there, MABA bar, that force is in a direction opposite to the direction of motion. Body is moving in this direction, and this negative sign indicates that in whatever direction the frame of reference is moving, okay, to that in opposite direction you will have this pseudo force. That's why when bus is moving in the forward direction, you experience force in the backward direction. When bus is suddenly stopped, when your car is suddenly stopped, okay, then what happens? You will experience a push in the forward direction. Is there anybody pushing you from the backside? No. But you do experience a force. Such a kind of forces, such a kind of unreal forces, such a kind of forces which are not exerted by anybody or any other body. Such a kind of forces are called as pseudo forces. Okay. So with this, I will close the session, students, and in the next session, we will deal with the applications of this pseudo force. Okay. Thank you, students.